Hello,
Yes, yes, sir.
am I audible?
Yeah, yeah.
Okay,
Right.
fine. Just wait for 10 minutes to join someone else, then we will start.
Okay. Okay.
Hello,
Yes, sir.
yeah. So, in this week, mostly the concentration was on active materials. So, we can tune the response of the meta materials to the different resonance. Uh, okay,
Yes, yes.
so regarding this, many things are discussed like performance matrix of the tunable metasurfaces. So the performance matrix of tunable metasurfaces depends. So performance matrix of tunable metasurface. So it depends on some modulation depth, that is defined delta r by r or delta t by t, where delta r is the radius, like some let's say ring, so the radius of ring, and then we the thickness of this also depends on this, and some modulation speed, and third one, it depends on energy consumed, because when we give some energy to the system to activate it, so it is also important to get higher output than we give the energy, so the energy consumption of the device should also be less. Third one is wavelength of operation. So wavelength of operation is like there are electromagnetic spectrum from infrared to ultraviolet. So there are many different region, like visible region, IR region, mid IR, terahertz region, gigahertz, microwave region, like that. So it depends on the wavelength of operation in which region uh, we have the resonance of that material. So we will tune the performance of that metasurface depends on that things, and also like the laser cavity, sir, describe our laser cavity, right?
Yeah.
So in the laser, you if you go to the electronics, so you must have heard about the amplifier, right?
Mhm.
What it does, the amplifier does, or I can say oscillator. You must read about oscillator, right?
Mhm.
So the oscillator made with two things. One is amplifier, other thing is feedback system. One feedback system is also should be there. So this is something like we have one amplifier here, and then this is output, and one feedback feed the system, and from here we input the thing. Okay, so same thing is happens in the laser. So in laser we have one cavity, okay, which act as an amplifier, okay, and then we put some gain material inside that. So what the gain material is, gain material provide the feedback of the feedback to the cavity, so it the whole system is work as an oscillator, uh, and when this oscillator emits the coherent, very high intense coherent light, then this system is known as laser system. Okay, so
Mhm.
you can read in detail. One video lecture are there on the laser system, MR Senoy, uh, from IIT Delhi. You can find the YouTube lecture. So he explained very precise and very in detailed way, or and comparison with the electronics to the laser, semiconductor laser, like that.
Hmm.
Okay, so these are all laser. One other concept, we can say this radiative absorption and emission. Like, as I told you, this oscillate in the cavity, one cavity. This is cavity. Here is the fabricated cavity, or any type you can cavity, take the cavity. And other thing, the laser gain material. So what is the gain material? So in the whatever put this material, gain material, there are some phenomena happens, which is explained by Einstein coefficient, and so these phenomena are absorption, emission. Okay, so let's say some material has one ground state. Okay, and this is the band gap, and we have one excited state here. Okay, so if some photon is coming to this system, so whatever hole or electron in the ground state, it will go to the excited state, right?
Hmm.
And it is absorbed. So this phenomena is called absorption.
Yes, sir.
Similarly, if we have the same system, and after absorption electron is somewhere here, right?
Hmm.
So this
Yes, sir.
electron can transit from here to here again. Okay, so
Hmm.
this phenomena is called emission. But this emission is divided into two parts. Either it can be spontaneous, or it can be stimulated. Okay, so what is the
Okay.
difference between this spontaneous and stimulated emission?
Yeah, one is like stimulated means we are putting some external influence to get a desired frequency output or something like that. That is, we are stimulating from outside.
Okay, but like, if we are giving one photon to this. Okay, and this is absorbed by this material, and this electron is only excited to this mm, state,
Hmm.
and the same electron when comes to this one, so this is giving emission, the whole process. Okay, so in this way we are also exciting this with the same the photon to the material, right?
Yes.
So, and you are saying that we have to uh, excite by something in the stimulated. So if you combine these two process, so these are some simultaneous process, right? So
Yes.
we are also exciting here with some photon, and then that photon absorbed and electron go to excited state, and then the photon also coming back to the ground state. Then only it give the emission.
Yes.
So, but what is the difference between this emission and this emission? In this emission, one photon is coming, and then it emits, right? So why
Yes.
we always draw two photon in the stimulated, while in emission we only draw one?
Hmm.
The reason is, we we are giving the photon, and when the absorbed photon and the emitted photon both have the same phase, same frequency, then only it is called stimulated emission. Okay,
Yes.
so this is the that spontaneous is randomly. So the what it is called, mm, coherence or this frequency and the phase lag, all these thing is not noted in the spontaneous emission, but in stimulated emission, whatever the input photon comes, the in the same phase the output photon will be there. Okay, then
Yeah,
only we
actually, see,
uh,
if you can I ask something like,
uh, yes.
yeah, actually, see, like whenever we in this kind of quantum explanation of this kind of systems like two-level laser or something like that, we write in general, like we write the electric field or magnetic field of the light like e to the power I omega t minus kx form, right?
Yes, yes, yes.
Okay. Now the e to the power I omega t plus minus kx whatever is there, the whole thing is phase.
Whole thing is
Phase.
yes.
This is a phase part.
Mm.
Now, like if you're in the stimulated emission, okay. Now this is quite understandable. Like why the frequency is matched with the uh, input wave. But if like if we are considering like if the whole thing like it is I omega t minus kx, okay.
Okay.
So from what aspect the whole phase, the whole term like I omega t minus kx or plus kx, these two things will be equal for both the photons.
Okay. Actually, this is the two level system. Okay.
Yeah.
But
Hmm.
if you go to the third level system, three level system, then you can say the more precisely you can understand like what is happening in the stimulated emission or some lasing. You know there is some population inversion term is used, right?
Yeah, yeah, right.
Yeah. So so for the stimulated emission, you must create some population inversion first.
Hmm. Yes.
So in population inversion, what happens? Like let's say there are some meta stable state here, and the what it is called lifetime is very high, very long for this state. Okay.
Yeah,
So
the upper state.
yeah. So whatever electron absorption happens, it will go to this state. Okay,
Yes.
and then from here this will come to this state. If you pump
Yes.
continuously, electrons go to on the this state, but they will not stay on this level. They stay on this stage. Okay,
Yes.
so at
Right.
a time the n2 value and here is n1 value, then if n2 value is greater than n1, okay,
Hmm.
then this is the condition of population inversion. And
Yes.
if all the electrons come from the same stage, then you can say they are on the same phase and the same frequency, right? At the same energy.
Okay.
Got it?
Yes, but here another thing like
Hmm.
um, there might be something like many of these photons. Okay,
Hmm.
suppose there are 100 protons or that sorry 100 electrons are coming from the upper side from
Uh,
N2 and coming to level N1.
yes.
Okay, now there might be some of the electrons which are coming from level 2 to level 1. They
Hmm.
might be stimulated, but they are just naturally spontaneously coming from
Yeah,
N2 to
yeah. Spontaneous will
N1.
also come, but then one laser, uh, you know that like if we here is the input
Hmm.
power, okay, and here we can say this output power, or you can say that whatever peak is FWHM if we plot, okay. Then
Hmm.
what happens if you pump little bit low input, okay, the output will be somewhere like that, and at some threshold value this output pump like that. You saw this type
Oh,
of curve.
yeah, yeah.
Yeah, so what happens in this curve, in this region, okay, or you can
Hmm.
say in this region there is only spontaneous emission will be happens. So it also depend
Okay, so
your excited
after some
state.
time it will exceed
Yeah,
the
yeah, then
basically
only this population
overshadow the
erosion
speed.
condition will satisfy.
Okay, okay, got it.
Okay, and
Yes, yes.
if you read some basic diode, that light emitting diode or something, in that one the
Hmm.
diode region works in this region only, and after that this region is the for the laser things
Yes, sir.
in the same curve, if you see. Okay,
Yes,
so
sir.
this is something basic about this stimulated emission and spontaneous emission. So
Hmm.
all these emissions can be explained by uh, the coefficient given by Einstein called Einstein coefficient.
Hmm.
So if you check the rate of change of number of electrons in this state to this state, so dn over dt, you can write something minus v12 and n1 into rho v. So this is the electron density, you can say, and this is the total
Hmm.
number of electron, and this v12 is the known as Einstein coefficient, which is related to absorption only. Okay, similarly
Okay.
other absorption, sorry, other Einstein coefficient is a21 and v21. So v21, so a21 and v21 is something related to the spontaneous emission, and this is stimulated emission. Okay, so but you can ask like that, we have absorption, we have spontaneous emission, we have stimulated emission, but why not we have stimulated absorption?
Yes, sir.
Do you think about that?
No, no, it didn't came to my
So
mind.
it should be stimulated absorption also, right?
Yeah.
But Einstein gave only three coefficient. One explain absorption, second explain spontaneous emission, and third one stimulated emission. Because stimulated absorption is not possible. Why?
Stimulated absorption.
So the emission happens when the electron goes higher energy to lower energy, right?
Yeah, yeah.
Is it possible that we have lots of electrons or in the lower energy and they will go suddenly to the higher energy?
Yes, that is not possible.
Yeah, yeah. So the stimulated absorption is not possible.
Yeah, right.
Okay.
Oh,
So similarly, you can write the equation like we have in this figure. If we have n1 and n2, and also the energy of this one is E1, this is energy of E2, right? Then
yes.
dn2 over dt, this is the rate of change of electrons in the excited state, right? So
Yes.
this is something related to emission, right? So if,
Yeah.
and this is also proportional to n2, and there should be one coefficient, that is 1, sorry, a21 means 2 to 1. Okay, second level
Okay.
state to 1 first step. So this is related to emission, okay, emission
Yes.
constant. And similarly, if you write for the stimulated emission, then again dn2 over dt, it will be proportional to the n2, which is the number of electrons in the excited state, and the density of, because it is very important for the stimulated emission. Until this n2 will not greater than n1, the population inversion will not happen and stimulated emission will also not happen. So this will comes one coefficient v21. This is the Einstein coefficient, and Einstein drives these equation. You can find in the reference book which is given in the lecture. So, and then the relation between these uh, coefficient, Einstein explained the different phenomena like black body radiation and the laser. They are also called some laser equations. Okay,
Hmm.
so this is something short overview of the radiative absorption and emission, which is well explained in the lecture. So now I will come to the first question of tutorial. So in the
Actually,
question,
sir, doubt here, like,
yes,
see, in this week, like, if, the so many concepts sir has taught, like,
okay,
in a very fast pace. Okay,
mm,
so like, now what kind of theories that we should read for the answer those questions properly? Like, see, because first he started with uh, yeah, first he started with those array thing, like. Tuning mechanisms and all. Then we went to laser. Then we studied some nano laser, something like that, and how we can
okay,
minimize those things.
okay,
So there are so many things which are not available. Like, in general, we didn't go through these things. Huh? So
okay.
from where we can, like, go through the books, which books
So
were suitable for.
I can clarify, like the basic concept you can read from the books, okay, and then as sir said that miniaturization of the optical devices and all these things, so we have to minimize the size of the laser and all these things, right? So
Mhm.
all these concept is well, sir have the slides. On the slides sir have some paper references for the each slide.
Okay.
Okay, so the all explanation is given in these research papers only, because
Okay.
whatever examples are said give the reference is from these papers which is cited in the
Mhm.
slides.
Okay, okay, got it.
Okay, so you can
Yes.
go through that thing also. But if you have some specific question like how to miniaturization and all these things, so that you can ask me also. I will try to give the answer.
Okay. Actually, I have some few queries regarding the non-Hermitian portion. So, if any, is there any problem that you are going to discuss in from the previous year questions? So, during that time, I will
Non-Hermitian,
ask
I
the
think
question.
there is not much question.
So, you just finish the discussion. In that case, I will
Okay, okay. At the end, I
ask the
will
question.
just explain something related to Hermitian
Okay.
and non-Hermitian system.
Yes.
Okay.
Okay.
So the question one is like there are uh, figure four figures. A is this is level one. This is level two, and there are holes. And here is the electrons in this state. and the simply one arrow is down. Okay, so this is figure A. Similarly, figure B. So in this one state is there, and then it go like that. Okay, similarly in C figure, so just the first one is absorption, second one is spontaneous emission, third one is stimulated emission, and fourth one is trap assisted recombination. So just you have to identify the correct schematic corresponding to the mechanism. So first one, what is the relation between A and what will be the mechanism in this figure?
This one would be spontaneous emission.
Spontaneous emission. Okay, and B?
B is trap assisted option.
Yeah, and C is?
And C is one like
C is
absorption.
absorption हो गया, and D is
And D is three.
stimulated emission. Okay, so this
Yes.
will be the right match. Similarly, the spontaneous emission process in an atom. This was the first question. Question 2 is the spontaneous emission process in an atom is governed by Einstein coefficient. Which coefficient it is?
The spontaneous one. A21. It is B21.
A12 to B12, third one is B21, C is A21, and fourth one is okay. So this will be the correct answer, A21.
So the spontaneous emission process. Okay.
Yes, spontaneous emission process.
Okay.
A21 previously told.
Okay, fine.
Similarly, question 3 is the stimulated emission. Then what will be the coefficient?
So B21. I think this one
Yeah,
would be B21.
yeah, this will be B21. Sorry. Question 4 to 5. The radiative lifetime of an atom excited state 2 is given by tau is equal to 2 into 10 to power minus 9 second. Okay, so the question is the time which the carrier density in the excited state reduces 1 by E times initial value is. Your option is 5 into 10 to power 9, 8 into 10 to power minus 4, 3 into 10 to power minus 9, 6 into 10 to power minus 8, and 2 into 10 to power minus 9. Five minutes to solve.
Give me a second.
Yes, 2 nanosecond is the answer. How you solve it?
E power minus t by tau, sir.
Sorry.
E power minus t by tau, directly proportional to e power minus
Yes,
t
yes,
by
yes.
tau.
So the relation you can find n2 is equal to n2 at time 0, yeah, n2 at any time, into e to the power minus t upon tau, right? So uh, sorry, this is the initial one, right? So n2 0 you can write. So n2 is equal to n0 ye. So you can find n20 ye is equal to the power minus t by tau. Minus t by tau is equal to 1 minus 1. So t is equal to tau. So t is equal to 2 into 10 to the power minus 9. Okay, this will be the answer. Similarly, question number 5. The Einstein coefficient A21, how you will find for the same system?
E21 is 1 by t most probably.
Sorry?
Inverse of the lifetime.
Yeah, A21 is
of
1 by tau,
spontaneous
right?
emission.
So A21 equal to 1 upon tau. So you can find this 1 by 2 into 10 to the power minus 9 equal to 5 into 10 to the power 8 second inverse. So this will be the answer. Question 6 is the rate equation for stimulated emission process is. So let's consider this is stage 1 and 1 is there, and this is 2 and 2 is the carrier concentration in the excited and ground state respectively. Then what will be the rate equation for the stimulated emission? Yes, right answer. dn2 over dt equal to minus p21 and 2 u of mu. Okay. Any question on this one? For question 7 and 8, there are one structure like that. So this is gallium arsenide, this is aluminum gallium arsenide, this is structure A. Okay. Similarly, structure V is this is gallium arsenide, this is aluminum gallium arsenide. Similarly, structure C is EV and this is EC. This is gallium arsenide only. So question 7 is referring to structure A, which of the following is true? So we have a statement like band gap of gallium arsenide is larger than band gap of aluminum gallium arsenide. V is band gap of gallium arsenide is smaller than band gap of aluminum gallium arsenide. C is band gap of gallium arsenide is equal to band gap of D is refractive index gallium arsenide is greater than aluminum gallium arsenide. E is refractive index of gallium arsenide is less than aluminum gallium arsenide. F1 is refractive index is equivalent. So which one you will choose? In this structure.
Yes, I think B and D that you have written here, option B and D. That is the refractive index would be higher.
Yes.
Yes. And since it is inversely proportional, and B is it is evident from the
in the figure you can say like this is band gap is less than band gap of this one, right?
Yes.
And And the other question is, which structure you prefer for fabrication of gallium arsenide laser, and why?
Yeah, for lasing, I think the first one would be suitable because like the electrons will be trapped in if we whenever we are giving some current. Okay, so it will help to create the population inversion in the middle. We have GS in the middle
Yes.
between the metal gases.
So structure A, as it confines both electrons and photon, क्योंकि ये डबल हेटेरो स्ट्रक्चर दिस वन. So if we the electron will come, it will go to here, and from here to here, and whatever it will emit, it will not absorb again, because band gap
Yes.
is more than higher of this band gap. Okay, you can think like that. So structure A is the suitable for laser. Question 9 is, the active region of diode laser is defined as. What is the active region of diode?
Active region of diode means like the laser diode.
Yes.
Acha, like is it the gain medium or something like that?
Yeah. So do you know the mechanism of LED or laser diode?
Uh, in that case, like diode means like binary junction, na? One side
Yes,
is
yes.
P and in that case, like they will recombine in the junction, and we will get some due to the recombination, we will get some photons. Something
Yes.
like this could happen.
So what is the active region? Then you will say the active region is the recombination region, right? Where the
Yes, yes, okay.
carrier recombines, thereby contributing to the useful gain and photon emission, right? So the recombination region is the active region of the diode laser.
Yes.
Okay. Question 10 is the essential figure of merit to equivalent the performance of tunable metasurface are. Which one? Bandwidth, these modulation strength, C is heat conductivity. Of the material. D is modulation speed. And E is size of metasurface. So tunable metasurface you know, right?
Yes, sir.
So how will you define the figure of merit of
Modulation strength you just already mentioned,
these?
modulation
Yes.
depth and modulation speed. Both of them you have mentioned earlier.
Yes, yes. So these
And
two only are the uh, figure of merit to see
yeah,
band.
I think
Yeah.
will it cover option A also, because you mentioned about the energy, how much energy it will consume, something like that.
No, no. So how will energy they consume, not the how much energy they produce, because bandwidth is related to the loss, right? So some radiation loss, not the inner.
Okay. Correct.
Question 11 is the primary mechanism for achieving dynamic permittivity modulation using ITO is. So A option is rearrangement of constituent atom on application of a voltage wise, thereby changing state from amorphous to crystalline. And second one is axis carrier generation due to the application of external magnetic field. Third one is rearrangement of constituent atom on application of thermal energy, thereby changing state from amorphous to crystalline. Third one is injection of carriers at the interface due to applied voltage wise. Fifth one is physical expansion and compression on application of external stimulation. Should I write all?
No, no, it is not required. Like in this case, I think the variation of uh, electric or magnetic field can change the permittivity.
No.
Okay, so in that case, only the thermal thing is possible, from changing to amorphous to crystalline or
No, no,
crystalline to amorphous.
no.
Sir, ITO means
Sorry?
ITO means
ITM is indium tin oxide. V is excess carrier. So the primary mechanism is injection of carriers at the interface due to the applied voltage rise. This is the primary mechanism for achieving dynamic permittivity modulation.
Okay, okay.
See, mm, this is band gap, right? So in band gap the delta epsilon is related to this band gap only, right? So whenever we apply the voltage wise, okay, then some carrier will inject and the band gap will change little bit. If it has two bands, so for PN junction B, if you apply that, this formula will go up, right? So it will change the effective permittivity inside the crystal. Similarly, question 12 is some of the prominent permittivity tuning mechanism are using which one. So these things are explained in the lectures. Permittivity tuning mechanism. So one we use PCM, that is phase change mechanism, okay, or second one mechanical actuation, and third one is photo carrier excitation. So which one is waste? Waste mechanism is good. So you have to arrange the order of prominent permittivity tuning mechanism. So in that one, this is number one. So phase change, material will phase change, like it is go to the crystalline to amorphous or amorphous to crystalline by applying some voltage or some heat, then the effective permittivity will change, right? So first one is this phase matching, phase change mechanism, and then photo carrier excitation is second one, and the worst one is mechanical actuation. So tutorial questions are over. If you have some doubts, you can ask now.
Sir, actually, I just want to know about the non-Hermitian systems that sir has discussed in the class,
Okay.
like providing the material losses and gain simultaneously in the same structure. So, can you please just explain how we can do these things and how these things are helpful?
Okay. Just some brief how sir explain, like which system they consider. So in quantum mechanics, if you know some quantum mechanics,
Yeah, a bit.
okay. So in quantum mechanics, this psi should be Hermitian. This is the first condition, right? Psi is the Hermitian system, Hermitian function.
But a condition about what? Like,
Hmm? For the wave function which satisfy the Schrodinger equation, So in Schrodinger equation, this psi is Hermitian, right?
This wave function or that I think the operator is defined as
Sorry,
Hermitian
sorry,
or
sorry,
not.
sorry. Operator. Sorry, operator is.
Okay.
So this operator is Hermitian, right? So in the practically, what is the operator? In practice, like
Representing
whatever
some
our
physical
system is,
parameter
that
like
is the operator,
momentum or
because
potential.
this change the phase or something which we keep the light. Okay, so the cavity should be Hermitian or non-Hermitian.
Like if we want some real systems, okay.
Okay,
So in that case, since Hermitian matrices will have real eigenvalues and eigenvectors,
okay.
not eigenvectors like eigenvalues. So in that case, if we want to design some real system, it should be Hermitian.
This will be non-Hermitian always.
Okay.
Okay, so like if you read about Fairy parrot, right?
Okay.
So in Fairy parrot, you consider R is 100% and this reflectivity is 100%, right? Both mirrors. So
Okay.
this is ideal case. There is no loss.
Okay.
Okay, and whenever there will be no loss, that system will be Hermitian. Because if you write the Schrodinger equation, so in Schrodinger equation, if you put the imaginary part of that, what it is called, mm, whatever this, mm, what it is called, B is potential, right? So if you put the
Okay.
potential as the imaginary, not imaginary, the complex function, right?
Okay.
Then your uh, solution, or which is called eigen energy, right? This will be also the complex. And if your, sorry, in the Hermitian operator, the solution will be real, right? Not the imaginary.
Okay.
In non-Hermitian system, the solution will be imaginary. So this is related something like that. Uh, can I explain you in the next class? Uh,
Okay, okay.
by
No issue,
preparing
no
for
issue.
you.
Actually, in our in our assignments, okay.
Mhm.
So there are some questions that has been asked like with some material. Suppose there are two, three materials,
Okay,
X, Y, and Z. Okay.
okay,
So uh, they have something like suppose here sir has given GA, and P 1 - X, something like that.
सॉरी
So
फिर बोलो मैं लिखता हूँ अभी.
okay.
हाँ.
Uh, like yes, can you see the question? Like you also have the access to the course, no?
No, I don't have the current assignment. I don't have the access.
Okay, okay. Can I just copy paste the
Yeah, yeah.
item here?
Yes, yes.
Okay, just give me 2 seconds. Just few seconds. Sir, I have pasted the question here. So can you just tell us like how we can approach this type of questions? Like what is the
Okay,
because
okay.
in class, I think sir didn't address this kind of ideas or something like that.
The band gap of third and fifth semiconductor alloy aluminum minus X varies with the composition according to EGX is equal to this one x square. The band gap is direct for x is equal to less than 0.43, the indirect or larger value. The range of wavelength that can be usefully be obtained from aluminum gallium arsenide emitter is. So see,
Just I just want to know like how these things are related, like how to approach this problem.
so x is less than 0.43, the band gap is direct, right? And indirect for larger value. So the limit is x equal to 0.43. So if you put x equal to 0.43, what will be the band gap? You just find that, and then you just find the whatever the wavelength corresponding to that, because the wavelength only for the direct band gap, because if indirect band gap will come, then also the phonon excitation we need, you know that.
Yeah, that's why he has given that condition like k equal to 0, so that
Yes. So x, if x is equal to 0.43, and let's say EZ is given by 1.42 plus 1.087 x plus 0.438 x square. Okay, so your easy min कितना होगा when x is equal to 0. Okay, so x is equal to 0, 1.42, this is the one wavelength is allowed, because only direct band gap is allowed, is useful in the optics of photonics, right?
okay.
So 1.42 corresponding to this 1240 divided by 1.42 is something, this is something wavelength lambda 1, right?
Okay.
So easy max, which has the direct band gap, is 1.42 plus 1.087 into x. X is 0.43 plus 0.438 into 0.432 square. So this is 1 lambda 2. So only this to this is range is useful. Okay. So
Okay.
see, like silicon is also used in photonics, since silicon is
Hmm.
indirect band gap. What is the drawback of the indirect band gap? Like if your band gap is direct, the electron recombination will be only which is the photon given by you by only. Okay, if this is some
Hmm.
indirect band gap
Hmm.
like that, then this is the your optical whatever you giving the photon, but electrons should go here to here. So for that you need some momentum mismatch, right? So this
Yes,
momentum
sir.
mismatch only is given by this some phonon or something in the crystal lattice. So you have to also excite some phonon modes to reach photon here to here for the recombination or excitation process. So this will be little bit unuseful for the optical application. So that's why we will say that only direct for the direct band gap these material are useful. So you just find the range where the direct band gap is here, and that will be your useful wavelength range.
Okay, sir. Thank
Okay.
you.
So for non-Hermitian optics, if you want to understand, I got one paper from Advanced in Optics and Photonics. You can read it, or I can
Okay.
discuss it in the later lecture.
So, okay, sir, you can just tell me in the next class. I think that would be better for me to understand.
Okay, okay.
Or can you just share the GUI in the chat box so that I can also have a look on that paper?
Mm, this is the topic is non-Hermitian optics and photonics from classical to quantum. This is the
Okay.
topic of the paper, and this is in Nature, Advanced in Optics and Photonics journal,
Okay.
and author is Lan Yang. The last author is Lan Yang. Some Chinese paper is. So basic idea is the Hermitian operator we know, right? So any state of quantum system is represented by unit norm vector in the Hilbert space. So observation which are the outcomes of the physical measurements are associated with the operators, right? So
Actually, sir, the concept of Hilbert space is I don't know. So,
Hilbert
sir, I think
space.
it will be better if you can tell me in the next class so that
Okay,
I
okay,
can
okay,
understand.
okay. I will explain it in detail. Some PT symmetry and all these things are here to explain the
Okay.
Hermitian and non-Hermitian system. So basically, if you see the Hermitian system, there is PT symmetry is there, but for non-Hermitian system, this PT symmetry is will broken. Okay,
Hmm.
one is the this thing, and due to this PT symmetry broken, some exceptional point will come, and some bound state in continuum, and all these things will come due to this non-Hermitian system.
Okay, sir. And sir, I just have another query. Like
Hmm.
in the class, sir was sorting out that why we should minimize the laser.
Sorry.
Sir, why we should minimize lasers?
Okay.
Okay. So there I found something like in the class he has shown like uh, image of there is a mode 2. Okay, sorry, this is mode 0 and this is mode 1. Okay, so in large in a laser which is having some larger area or something like that,
Okay.
the dimensions are large. In that case, like he has shown some images of higher order modes like second order or third order modes,
Okay.
and in the graphical representation he has shown like if we are syncing the structure, okay, we are leading to a single mode. Okay, so my question is here like can we have like higher order modes in the nano lasers as well?
Yes, we can
So,
have.
so how
So
these things are coming like
so see,
in that small area?
it
Hmm.
depends on how small we need. Okay, if you are putting, like, if you see the old lasers, these are very long lasers, little bit some meter size laser. Okay,
Yes, sir.
but if you see your phone chip is around 7 nanometer, right? The minimum
Yes, sir.
chip. So if you need some laser on that chip, then how can you put that meter size laser on that chip? So you have to also minimize the size of that laser also, right?
Yes.
So the one thing is, like, if you saw the sorry, if you saw this Fabry-Perot cavity, okay, so
Mhm.
this is very large laser in comparison, and some other type of cavity you should use, like some disc resonator are there, some ring resonators are there. Okay, because for the
Mhm.
laser, what you need, one cavity is there. Then the second thing is you need some gain material, right?
Okay.
So for the to miniaturize the laser, first you need that cavity, so that cavity take the form of the disc.
Yes.
Should I write right? So like you have this disc, right? And or you have two mirrors. So this is the type of Fabry parrot cavity, and this is something called WGM cavity. Okay, this is another concept. So you can, as you reduce the disk size, the radius of disk size, the FSR will change. You know the FSR?
So what is it, sir?
FSR, free spectral range.
Okay.
So like if your cavity is very small, so let's say you have something like this. So this FSR, and if cavity is, so this FSR. So see, this is one mode, mode 1, and this is mode 2. Okay,
Okay.
so mode 2 will be there, but at a higher spectral space. So maybe you need only this much spectral range. Okay, so within this
Okay.
spectral range there is only one mode.
Oh.
So uh, your question was like ki, higher mode will also be there, but we will use the fundamental mode.
No, my question is like if I require like multiple modes. Okay.
Uh,
Suppose in different application it is required like to
okay,
distribute the energy in different patterns.
okay.
So, is it possible in nanoscale also to generate like first order mode, second order mode like
Yes,
this? That was
we have many, not only one mode. If you fabricate some structure, you will not find only
Mhm.
one mode. You will find
Okay.
some higher order mode also, but you have to filter that by restricting the cavity dimension.
Okay.
For example, if you have this disk, okay, so for WGM mode, the perimeter is the length of the light which travel. Okay, so this is 2 pi r. It should be m lambda,
Okay.
2 pi r n, you will say. So if you change the radius, so m will change, right? M will be 1 2 3, whatever mode is there. So all the modes will be there inside this cavity. Okay, but
Okay.
on the depend of your application, you will choose only that mode only.
Okay.
Okay, so this is not true that only one mode will be there if we make some laser. There will be several mode. Like uh, if you, this nano pulse laser, you heard about that pulse laser. So
Yeah. Pulse laser.
what people use, if you need laser of 1032, okay,
Hmm.
so the cavity will be same, 532 laser will be there, and the second harmonic will be 1032. So if you buying one 532 laser, if you take the spectrum around 1032, there will be one another peak, that is called second harmonic peak. But in general we are not going so far for our characterization, so that's why we are not able to see that mode 1032. We cut that thing. Understand what I am saying?
Oh.
So
Yes, sir.
it depends on your application. If your application is limited to only this mode, you will entertain
Mhm.
only this mode, you will not entertain to this mode.
Okay, sir.
And also if you like let's say some waveguide is there, and waveguide width is on this axis, and this is some n effective which I plot earlier also. So your first mode will be somewhere like that, and second mode will be like there. So if you choose some the width of the waveguide greater than this one and less than this one, so only one mode will be there. So yeah,
Okay.
by using this dimension we can cut the higher order mode.
Okay. Okay.
Okay.
Okay, sir.
Okay, so for non-Hermitian, sorry, I will write. I will prepare on this one for the next thing. In addition
Yes,
to
sir. Helpful for me, sir.
the tutorial. Okay.
Okay, sir.
Okay.
Sir, one more thing, like if you don't mind, the what app you are using for this for writing? Like actually, I use OneNote, but in OneNote I can't copy paste the drawings. Uh, is this a different app or?
This is good notes.
Okay, okay. Is it native for Apple or it is also available for Android?
Uh, it is, I think, available for Android. I think I don't know. I have to search
Okay.
for that.
Okay. I will look into this. Okay, okay. Thank you.
Okay. Okay. Thank you.
Okay, sir. Thank you. Thank you very much.